So without further ado, let me go ahead and introduce our speaker today. So Dr. Matthew Siegler is presenting the seminar, and he grew up in Wayne, Illinois, which he noted for the record is very close to the Fermi National Accelerator Laboratory in Batavia, Illinois. He's trying to draw a lot of connections today to this department, I think. He double majored in physics and in film at Cornell University, where he also became heavily involved in the 2003 Mars rover missions, as well as summer internships at Fermilab and CERN. So if you like what Dr. Siegler has to say today, keep in mind you too can apply for fellowships and summer internships and things like that at labs like Fermilab and CERN. After a year with the LHCb experiment at the University of Zurich, Dr. Siegler felt the pull of Mars once more. He headed to Los Angeles, where he did Mars-related laboratory work at Caltech, and then moved on to UCLA for his PhD in planetary geophysics. There he studied lunar ice, thermal modeling, and the orbital evolution of the moon. He then came to the Jet Propulsion Laboratory, JPL, as a postdoctoral researcher, and then as a staff scientist in planetary geophysics. The Planetary Science Institute gave him the freedom to move this work to SMU in 2015, where he's now a co-investigator on Mars 2020, Mars InSight, the Lunar Reconnaissance Orbiter, OSIRIS-REx, and the upcoming Viper lunar rover, which I'm sure you'll tell us all about today in some way or another. So please, without further ado, welcome Dr. Matthew Siegler to speak to us about remote sensing the planets with microwave radiometry. Dr. Siegler.
Okay, hi, and thank you very much for inviting me. It's nice to finally, I think we counted, we're here for 6 years now, so I'm glad that I could come and talk with you guys. Just down the hall from you. I'm based in the geology building, if anyone ever wants to bug me. Yeah, so I thought this would be an interesting topic of kind of overlapping some of physics and the planetary astronomy that I work on. So with little ado, thanks for the introduction, and we'll get started here. So I basically started doing thermal modeling coming out of work that I had done for CERN. I actually designed one of the cooling systems for the LHCb inner vertex detector. And so in that, I was measuring thermal conductivities of all that material and such, and that got me into thermal modeling. And then I started applying that to soils on Mars. And then from that, branched off into the moon and ice on the moon and all this fun stuff. And so I've worked a lot with temperature measurements, thermal infrared measurements of objects. And more recently, I've moved a lot into the microwave remote sensing. Microwave is really exciting because no one's been doing it in planetary astronomy, really. Okay, it's been something that we've used for weather satellites and things like that. But it wasn't until actually the Chang E 1 and 2 missions that went around the moon a few years ago that we ever really looked at a solid surface from an orbiter or a lander with a microwave radiometer. And it shows some really cool stuff. And so based off of this, we've now started to develop a new instrument at JPL, which we hope to send to the moon sometime in the next 5 to 10 years. And so that's pretty exciting to work on. So just a brief introduction of some of the things I work on. So like I said, I'm working on all these different missions. I'm a participating scientist where I competed to be added onto the team for Mars 2020, InSight, and OSIRIS-REx. OSIRIS-REx, if you don't know, is the one that took a sample of the asteroid last year and it's bringing it back in September of 2023. So we have to wait a long time for projects too. The Mars 2020 rover is also taking samples that will come back from Mars, but probably not until around 2030. We would expect to get those samples back. The sample return rover isn't actually even designed yet. InSight is going to stay on Mars forever, and I'll talk a little bit about some of the measurements it's done. Actually, maybe I cut that part out of the talk, but if you're interested in that, let me know. And then I started as a PhD student. I started working a little on Lunar Reconnaissance Orbiter, and I have worked on it ever since. And then Viper is the new mission that's going to land on the moon in December of 23 and has a drill that's going to drill down for ice. And so I make all these models where we expect ice to be on the moon, and we figure out where to drill with that. And then there's a couple of these commercial lunar landers that are precursors to this mission that are going to come up in the next few years. And I'm on 2 geothermal heat flow probes from that, and then an infrared camera. So like I said, a lot of what I do is based around anything thermal on planets. Okay, so I do infrared remote sensing. I do thermal models of how, so here's the InSight lander, and we wanted to know how the lander itself was affecting the geothermal heat signal that we wanted to measure. And then I do global models too of here's what we expect the geothermal heat flow of the moon to look like, or here's the geothermal heat flow of Mars, what we expect it to look like. And these are from measurements from orbit around the moon and Mars with a thing called the gamma ray spectrometer, which is basically something that came out of Los Alamos lab, as a particle physics instrument, and has later kind of revolutionized our understanding of the surfaces of the moon and Mars. So we can measure things like uranium and thorium with that. And then from that, we can model, if that is representative of the subsurface, what heat flow would we expect? And then we go and measure it and compare our models to what we see. Most of my PhD thesis was about ice stability on the moon and Mercury. So we had some cool papers on that. So I make these great thermal models of where we expect ice to be on the moon and how deep it should be based on the temperatures on the surface. And then we model how it propagates into the subsurface. And with that, and looking at the orbital history of the moon, we actually modeled how the moon seems to have changed its spin axis about 3 billion years ago and caused the ice stability to change on the moon dramatically. Then I do a lot of modeling with volatile stability. So one of the things we were looking for with the OSIRIS-REx mission, this is asteroid Bennu, which is about a 500-meter asteroid that could, I think it has like a 1 in 8,000 chance of hitting Earth in the next 300 years. So that was one of the reasons we went there. We want to characterize the temperatures on its surface because that controls something called the Yarkowski effect, which is how thermal emissions off of the asteroid control how it moves with time. And so here's the dramatic sampling event last year. Then I do stuff with thermal properties. Like I said, one of the things that I got into originally was doing thermal properties measurements of materials, and got into looking at thermal properties of Martian soils and lunar soils. Here's some Apollo 11 soil they had, just to show you how dark the moon really is. This is the mare of the moon, and this is just when they flashed it with a camera. So it's pretty dark on the moon. And then, like I said, and we'll talk about today, I got more recently into microwave radiometry and what we can do with that. And can we use this both to look at temperatures below the surface to measure things like the geothermal gradient that I'm interested in, and then to measure where there might be subsurface ice and such. Okay, so what is microwave radiometry? So microwave radiometry is basically looking at things that we'll call microwaves, which I'm broadly saying 1 millimeter to 300 megahertz. If Joel were here, he'd probably say something different in the range. But anyway, it's a broad part of the frequency spectrum. It's kind of fuzzy in the literature sometimes, where what you call the boundaries of microwave and radio and all that. But when you're looking at a solid surface, the emission you see in the microwave both depends on the physical temperature of the surface, but also the transparency of the surface, how deep into the surface you're actually going to see. And so with this, when you have a semi-transparent medium like the regolith on the moon, you can actually see quite deep. All right, we can see to several meters with some the 3 gigahertz radiometer that was on the Chang E instrument. And so what we're trying to do then is develop, to look at the data we have and develop new instruments to see deep into the lunar surface. And then you can imagine if there's a chunk of ice down there, the temperatures might be different. The dielectric properties might be different. We could probably sense it remotely. And so it makes an ideal measure, instrument for looking at some of the things that I've been interested in scientifically. Okay, so microwave remote sensing isn't entirely new, but it is pretty new as far as what's been done. Some of the early temperature measurements we had on the moon were actually in the microwave, because you can't do infrared measurements from the Earth of the moon, right? Because the atmosphere is in the way. And so if you looked into the microwave windows through the atmosphere, you could actually see, map the temperatures on things like the moon or Mercury. And so that's where a lot of our initial understanding of the global properties of the moon came from. Then we pressed forward with other Earth observations in microwave. We did microwave measurements of other bodies, like here's microwave emissions from Mercury. Here's list Ganymede and Galilean satellites. And then the first NASA instrument that looked at microwave is the Juno microwave radiometer that is orbiting now around Jupiter, and pretty excited. Just recently had a flyby of Ganymede, one of Jupiter's moons. So hopefully we're going to look at that data when it becomes publicly available, and then also Europa to measure the heat flux there. What does microwave data look like? Okay, here is a picture of, these are maps of average temperatures measured at each of these things. We call brightness temperature is how we measure in microwave. So that's the axis label that I didn't put on here. It's brightness temperature at each of these different frequencies. Here's where they're coming from. All right, there's 4 different antennas on the Chang E 2 instrument here. And we can see that you're basically seeing temperature, right? You see it's cold near the north and south pole of the moon, and it's warm near the equator. And that's what I've been working on since my PhD thesis, right? Is working on with the Diviner instrument, which is one of the instruments on LRO that I'm a co-I on. We can measure temperatures at the equator of the moon are hotter and they're colder near the poles. All right, that's all well and good, but what more information can we learn than just the moon is cold at the poles and warm at the equator? And that comes into what we're actually seeing with the microwave remote sensing and what we can model with it. So basically, any warm body is going to emit microwave radiation depending on the wavelength that you're observing at, right? The physical temperature of the medium, and that is temperature not only at the surface, but temperature as a function of depth. And then the dielectric properties that radiation is coming up through. And so that all boils down to this term I'll use a couple times called the loss tangent, which basically controls how transparent the material is. It's a ratio of the real to dielectric or to imaginary dielectric constant. And then I'll show a few times these things called weighting functions, which are basically a visualization of that loss tangent that shows what depth you're getting radiation from. So here's this weighting function for, these are the 4 channels that we had on the Chang E microwave radiometer. So 37 gigahertz, high frequency, you're not going to see very deep into the subsurface. And so its weighting function piles up near the surface, and you're seeing mostly in the top few centimeters. 3 gigahertz, you can see down over several meters, right? Because you're penetrating more deeply into the surface. And then we can model what that would look like as far as data, right? So this is your thermal trumpet, right? So this is the maximum temperature as a function of depth, or the maximum temperature as a function of depth, and the minimum temperature as a function of depth. And then this is at a given time. So this is near midnight, right? It's not actually always at the coldest. There are some depths that are warmer at midnight than they are at noon, right? So here's the noontime temperature curve. You see that these depths here are actually colder at noon than they are at midnight. So you need to take into account that whole temperature profile with depth. And that you'll see animations of this waving around like that. And then we have our weighting functions. These are for 2 different frequencies. And then what I have here, the dotted line is a different loss tangent, right? So there's high loss material that has a lot of a mineral, ilmenite, that is very high dielectric loss. And so we don't see as deep with that material. And so we're going to see something closer to the surface temperature. Surface temperature on the equator of the moon varies by about 300 Kelvin day and night, or 300 Kelvin day and night. And so you get higher amplitudes the higher your loss tangent is. And that's what we see in this model here, right? We have a high loss tangent. We're going to see, this is the daily cycle. So this is noon and midnight. And we see that a high loss results in a higher physical temperature or brightness, temperature, amplitude. And so we can use this to model the data. Here's the data from the equator of the moon from the Chang E instrument. We can see that for areas with low titanium, low ilmenite content, we see very low loss tangent curve here. And then in white here is the areas with high ilmenite content. And you see that they have a higher physical amplitude. And that's what's going on with ilmenite. Ilmenite is this crazy mineral that has this, mineral structure here. You basically get a cation vacancy on the side of the crystal. And so your electron can kind of move up and down there and absorb, and it was very good at absorbing in microwave wavelengths that are on the scale of this crystal. And so what we can do is also look at how that weighting function changes as a function of ilmenite. And that's what we have mapped here, right? Is that what we're doing here is, I said, if you have high ilmenite or high titanium, you would not see very deep. So you'd see a higher amplitude, something like the surface. And then if you see deeper, you see a lower amplitude. And that's what we see here now, is now we have maps of basically the loss tangent of the moon, right? And just looking at the amplitude of the microwave data. So you can see places with very high ilmenite or high absorption, high loss, right? So that could either be due to an absorbing mineral like ilmenite, or it could be due to a rock, right? Which will also absorb, right? You can't see very deep into a rock. And so we can map those things as a function of depth. And so what we see here is that at different frequencies, we're seeing, here's the ilmenite map of the top millimeter of the moon from spectral observations. And we can see that we're changing, we're actually peering into the subsurface and how this mineralogy and density changes with depth. And you can see certain features, like here is this nice crater here. This is called Bruno crater. There's nice rays, ejecta. Those are all the rocks, small rocks thrown out of that crater. But as you get to a longer and longer wavelength, you don't see those anymore, right? Because your wavelength is too long and you're seeing right through those objects. And so with this, we can basically map something that's equivalent to both the ilmenite that we saw on the moon. So we're getting a mineralogy map of the moon, and then we're also getting a map of the rocks on the surface and the subsurface. They're kind of combined together, right? And because we've mapped the ilmenite separately with the spectral measurement in looking at visible spectrum, we can actually kind of subtract that with our models, and we can get just maps of rocks. But this is kind of cool because it's not just a map of rocks on the moon, it's a map of rocks on the moon at different size scales, right? So these are the centimeter rocks, and these are the rocks that are 10 or 20 centimeters there. And that's what I was showing in the last figure here. With thermal infrared, we can only map the rocks that stay warm through the entire lunar night. That's how we map something in a rock in the infrared. Is it's just something that has enough thermal inertia and high enough thermal conductivity and density that it stays warm through the entire 14-day lunar night.
Matthew?
Yeah.
Sorry, there's a question online from
Sure.
Tom. Can you just call on Tom?
Hi, Tom.
Yeah, hi. I missed something fundamental here.
Sure.
Over what fraction of the moon are you observing?
Okay, so the Chang E 1 and 2 missions were polar orbiters, so we're observing the entire moon.
I see. Okay.
Yeah, I will show some observations from Earth that we took later with the VLA and such, but and those will just obviously be the near side. But yeah, this is a projection of the entire moon.
Okay, great. Thanks. That helps.
Okay. Yeah, so this is the near side of the moon, the Mare that we see from Earth. And then here's the far side. So you see the moon has a lot of weird dichotomies, right? That all of the activity pretty much is on the side that we see from Earth. And there's not as much going on the far side, which is very interesting. Yeah.
Temperature for a given mineral, depending on the size of the whether it's satellite or like a rock.
Yeah, so he's asking, so does the brightness temperature we're seeing depend on the size of the rock? So that what we don't know is, does that loss tangent dependence on mineralogy depend on the total size of the crystal? So are we only seeing the large ilmenite crystals at 3 gigahertz, basically, versus the small ones? And that, I think we have to do more lab measurements to really know if there's some size dependence there. And then as far as the physical size of the rocks, that's basically what you can get out of comparing the different frequencies. Is that some, 3 gigahertz will see right through a rock this big, but it will stop a 37 gigahertz signal. So now we're looking on expanding. How can we expand our understanding beyond what the Chang E mission could measure on the surface? And could we send other instruments? So we're looking at the possibility of sending a small CubeSat, which is a refly of an Earth atmospheric instrument that's already orbiting the Earth, called Tempest-D, looking at the moon at 90 gigahertz. And Greenbank telescope in West Virginia happens to have a great 90 gigahertz mapper that we've been mapping the near side of the moon with. So we're trying to model this and compare that to our maps of the moon. And then that helps us constrain these models to understand what is actually going on with the moon and these microwave emissions, different frequencies. And so here we have the surface temperature model. These are models that Chang E here, who's my postdoc, help make these models up. Here's what the moon should look like at 90 gigahertz over the course of the month. Here's what it should look like at 3 gigahertz over the course of the month. And what's cool about this is you see, this is good revealing that we're seeing below that depth of the diurnal variations, right? So at 90 gigahertz, you're still seeing well into that depth, right? And so you see a day-night cycle happen. But at 3 gigahertz, I challenge you to pick out the day-night cycle going on here. It does vary by about 10 Kelvin over the day-night cycle, but it's a very small variation. You might see the colors change just a little bit. And so what that's showing is that at these long wavelengths, like 3 gigahertz, we're seeing deep enough that we're getting information about the moon below the diurnally variant layer. And that allows us to peek into potential changes in the geothermal heat production of the moon. Okay, so what we're talking about here is that, and then I don't know that I have, anyway, hopefully I have another slide explaining why geothermal heat is interesting later, but if not, I might go to it separately. But basically what we're seeing here is, right, we have these different weighting functions for different frequencies. So this is a plot for the weighting function at 3 gigahertz in the lunar mare, which have a lot of ilmenite in general, versus the lunar highlands, like the white parts of the moon, basically. We could see a little deeper into the subsurface. And then here's models of different geothermal heat profiles, right? So that was that maximum temperature and minimum temperature of the day-night cycle. And then below this diurnally varying layer, which goes about 50 to 70 centimeters on the moon, your temperatures as a function of depth are going to be controlled by the amount of heat coming from the interior. And that's exciting because now you can figure out what the moon is made of, right? We have lots of measurements of the surface of the moon or surface of planets, but what is the other 99.999% of the moon made of, right? One of the few ways you could tell is by looking at the radiogenic heat production of the body, because you have uranium and thorium are both what's called refractory elements. So when the solar nebula was there, they didn't get boiled off, basically. Okay, and other elements like aluminum and calcium are also refractory elements and make up a lot of the Earth too. Silicon is almost a refractory element. So you measure this gradient, you can back out how much uranium and thorium is in the bulk moon. And then from that, you can back out how much silicon, calcium, aluminum, most of the mineralogy of the moon then is explained for you. And so by measuring the geothermal gradient, you're understanding what the interior composition of a planet is. And that's fun to compare the Earth versus the moon. How did they form? And that tells us a lot about the formation of the moon. Was the Earth already differentiated into layers? Because these elements like uranium and thorium tend to concentrate in the crust and the elements that form there, right? And so if the moon or if the Earth had already differentiated into layers and then the big impact happened that caused the moon to form, right? That's a different story than if the Earth hadn't gotten to that stage yet when the impact happened. And then we compare this to what we're trying to measure with the InSight mission on Mars, for instance. We're trying to measure the geothermal gradient there to compare, well, how does the solar system vary? The disk forming the solar system vary as you get farther away from the sun. So that's the story behind what we're trying to measure this slope here. But basically, what we've found is that if we are seeing deep enough into the subsurface, we can actually measure this from space, right? We're remotely measuring the geothermal gradient, right? Traditionally, you have to drill down into the ground to measure this. But now we think on a body like the moon or Mars, we can see quite deep. We can't do this on Earth because there's a lot of water in our soil. Okay, it both causes this diurnal variation because we have water and air in the porous space of our soil. The diurnal and seasonal variations on Earth go 50 meters or something under the ground, right? And so you need to see very deep. And then also microwaves are very attenuated by water. And so we can't see very deep into the subsurface on Earth. But on a dry place like the moon or Mars, we can see low. And then because there's no air on the moon and barely any air on Mars, these diurnal variations and seasonal variations don't go very deep.
So Matthew, just a question.
Sure.
I'm sorry to make you repeat these.
That's okay.
Online, but there's a lot of discussion about the actual water content of lunar soil.
Mm-hmm.
Do you have to know what that content is to understand the data that you're getting from this in order to interpret it, or no?
Not well. I mean, we'd love to see a change due to water ice.
Yeah.
But I'm talking more about liquid water. Liquid water will have a very high loss. Ice actually has a very low loss. And so what we're trying to do with this instrument is we would like to fly it in a polar orbit around the moon, look at the poles of the moon, see a difference in the loss tangent, in that polar soil that we could relate to the amount of ice content. And so there you're comparing soil with vacuum in its pore spaces versus soil with incredibly low loss ice in its pore spaces. And so it's a question of whether we can differentiate that or not. So just to show you that the proof is in the pudding, that we can see this signal. Here's the 3 gigahertz temperatures at midnight on the moon. We can see that most of that is, it's cold at the North and South Pole at high latitudes here. And it's warm at the equator. If we take out that latitudinal trend, we can see that there's this one region again on the moon. There's the Mare on the near side here is a lot hotter in the microwave data. Most of that's because it's darker, right? A dark soil is going to absorb more heat. And so it's going to be on average about 10 Kelvin warmer, right? But if we even correct for that albedo, what we see is there are areas that are still quite a bit hotter in microwave brightness temperature here than we would expect they would be given their latitude and albedo. And there's areas that are a lot colder. These colder ones are due to, this is a temperature taken at midnight, right? And so if we have a high loss area, right, we're not going to see very deep. And so we're going to see something closer to the surface temperature, which at midnight is very cold. It's like 90 Kelvin, right? So this is Mare Tranquillitatis, where Apollo 11 landed right here. It's one of the highest ilmenite content areas on the moon. And so we see it is cold in this map. Now you could say, oh, well, these areas must be areas that are very transparent where we're seeing quite a bit deeper. But we could see that if we could see if they were lower density than they expect with the thermal infrared measurements. And we don't see anything like that. So these areas we think are special because they're actually having a higher geothermal heat flux. And that's exactly what we expect, right? I showed, plopped up this picture before. So this is the map from that gamma ray spectrometer instrument measured thorium. You look at the spectrum of high energy gamma rays coming off of the surface of the moon. We can actually identify different atomic structures there. So we see thorium or uranium or potassium we can map from orbit. We put those together to create a map of what we think the geothermal heat flux would be like if that represents a substantial part of the crust. And then we can compare that to the data. So here's a forward model of what we think the microwave radiometer would see at 3 gigahertz, given that model. This is all theory in here, basically. And then here was the data. And just to drive the point home that if we had 0 geothermal heat on the moon, we would see this. Okay, so we didn't have those spatial variations in geothermal heat or uniform geothermal heat on the moon. So we are, in fact, I think, measuring geothermal heat of the moon from orbit. And so with this, we can start to fit models of the geothermal heat of the moon. But we want to get better, and we really are only doing it with a single frequency. And so, right, to measure a gradient, really, we'd like to measure it in multiple frequencies. But so far, the Chang E 2 data we have can only see that deep enough at one frequency. There are a few places that give us hope that they might be so warm, such high geothermal heat flux, that we can see them even at a higher frequency. And so here's a few of them. You can see these guys that are bright red here. And not only are these odd places high geothermal heat flux, apparently, from the 3 gigahertz data, they're also ancient volcanoes, by the way. Right? So these are all the things that people have been mapping as highly evolved silica features on the moon, which means part of the crust has remelted concentrated elements of silicon in there. And so these are the closest thing we have on the moon to a real volcano. All right. We have a lot of flood basalt and such on the moon, very thin mafic volcanism, but this highly silicic volcanism is actually pretty rare on the moon. So here's what some of those areas look like up close. So here you can see this is what we call a rill on the moon. So there was an ancient volcano here and an outlet vent, lava flowed here for a few hundred kilometers. This is the Marius Hills, where there's these little dots all over, these little pockmarks there are teeny volcanoes that are all over the surface here. And we see them both as higher than expected brightness temperature in microwave. Here's another one that's very interesting. That's very similar to Marius Hills. Here's another thing that we think this has been mapped as potentially an ancient volcanic caldera, but it's kind of flooded over by the flood basalts of the Mara here.
And Matthew, are those maps that you're showing there at high resolution, are they coming from the same data set or a different data set? That upper right map, is that coming from?
No, so this is from the LRO,
Okay.
both the cameras and the laser altimeter they use. So it has a laser altimeter that looks and times the speed of light, return back, and then visible cameras.
So these are independent alternatives.
Yeah, yeah.
Okay.
Do you have a question? Yet?
Yeah, could you distinguish the material which is originally on the moon from the material which came from some asteroid impact?
So when you have an impact, most of the impactor is vaporized in the impact, right? This is what we sadly learned with Meteor Crater in Arizona. Behringer bought the land in 1905 or whatever because he was sure that there was a giant block of metal sitting underneath that crater. He drilled for 30 years and finally gave up and donated the land to the state. And that's why we have Meteor Crater as a place we can go observe. But basically, normally we don't have much remnant. You know, that's really turned into vapor, can go far, can be broken up into little pieces. So I don't think you have to have an extremely low grazing impact to have any hope of the impactor actually surviving and leaving. So I think it's more not a problem with the measurement as much as the the impact physics, I guess, is whether there would be anything to look at to survive. That is one of the, talking about the ice on the moon or Mercury. That's what we think is you could have a cometary impactor. And it's not that the comet happened to hit the pole of the moon or Mercury, but it's that water vapor got caught in the gravity of the moon or Mercury and bounced around and eventually caught its way in poles, which are cold fingers. So that's a way of looking at the survivor of an impactor, but normally we're lost in the, and the one we're most excited about is this area on the far side, which is kind of this weird little thing, right? There's nothing too dramatic about it, called Compton-Belkovich. It's a little feature. It's about a 20-kilometer wide, so it's a big feature, right? But it has been mapped as potentially being also a caldera-like figure, and its interest was brought to it because that gamma ray spectrometer basically found that it's one of the highest thorium concentrations on the moon. So what this seems to be is, like I was saying, when you evolve the silicon, when you remelt the crust, right, you'll get more silicon in the crystal structure, but you'll also get more of the heavy elements like uranium, thorium will get concentrated in that remelt material because they have big ionic radiuses, so they don't like to go into most compounds, and so they kind of get left behind in the melt, and so they're always stuck in the last melt material, and so you end up when you remelt the crust several times, you'll concentrate these elements. So this is telling us that there's some feature here where there was a lot of recycling of the crust or some supply from an area of the crust that was recycled coming up to the surface. And this is what it looks like in the 3 gigahertz data, all right? We've got this bullseye of hot, about 10 Kelvin hotter. So most of those features on the near side of the moon were only like 5 Kelvin hotter. And there's no weird density anomaly or rocks that we've seen. This H parameter is a measurement from the thermal infrared that we've developed for measuring density on the surface. And what's cool about this is not only is it so hot that it shows up in the 3 gigahertz at our longest wavelength, but seeing the deepest, we can also see it in some of the shallower wavelengths and potentially even in the real shallow wavelengths. And so we're actually seeing down into the surface. And we saw it also, this is the Chang E 1 or Chang E 2 mission, which was at a 50-kilometer orbit. And then the Chang E 1 had the same instrument, but it was at a 100-kilometer orbit. So we don't usually use the data as much, but it saw the feature as well. This is just a plot of temperature as a function of distance. So what's shown here is when something's far away, it's colder during the daily cycle. It's at the bottom end. And then when it's right on this hot spot, it's always hotter. So it's always hotter day and night. And the only way we could come up with to get something that stays hotter day and night is to give it a high geothermal heat flux. And so then we can model for a given geothermal heat flow, right? So we think the background of the moon is something like 5 to 8 milliwatts per meter squared of geothermal heat flux. And this feature, so now taking that as a reference point, this feature is something around 100 milliwatts per meter squared heat flux, right? Which is pretty hot even for Earth standards of geothermal heat flux. That's something that you would build your geothermal power plant on one of these things. So who knows? Maybe we've discovered where 400 years from now there's going to be a geothermal heat plant on the moon. But solar power is pretty efficient on the moon, actually, so we might not need it. But yeah, so this is an exciting window into a very evolved part of the moon. And so basically it appears that we're seeing geothermal heat flux in some of these very high heat flux places with these short wavelength radiometers. But now what could we see if we could see in longer wavelengths? So now we're taking these models of brightness temperature as a function of frequency for different geothermal heat fluxes here. And we can see that it causes a little difference at the low frequencies or at the high frequencies like 3 gigahertz. But now if we could see lower frequencies and see deeper, right? so just zooming in here, we can get a lot bigger bang for our buck, right? We can measure, if we look at 420 megahertz, which is this model here, we should see a larger signal for the same geothermal heat flux. And oh, here's finally a map of the thorium here again. So that's basically what's causing this model. And then we've been doing observations with the VLA, which is the big space telescope array in Socorro, New Mexico. So we've been looking at it at a couple different frequencies. Here's the map from 420 megahertz. And you can see that basically we're observing higher brightness temperatures in this exact spot. So we're pretty excited about this result, but here we are from Earth, basically measuring the geothermal heat flux of the moon.
So Matthew, what's the spatial resolution you can get with VLA measurements?
Around 120 kilometers or so on the surface of the moon, yeah. And that's what we're tempted to, so we may even do this for Mars as well, because on Mars, because it's a smaller object in the sky, we can actually use a bigger spacing of the antennas at the VLA and could get like 300 or 400 kilometer resolution on Mars, which is not bad for trying to do a measurement like this. And then that's also led into, so I won a grant to develop this instrument that we're now building at JPL to build a microwave radiometer to go all the way down to 300 megahertz to 6 gigahertz frequency. And so we're building that right now and competing it for some of these upcoming lunar missions to hopefully measure this gradient even more precisely, either from a lander or it could be on an orbit. Okay, so basically it's kind of cool. What we can see is that we think we are in fact seeing subsurface temperatures on the moon, and we can see deep enough that we think we're seeing geothermal heat flux, so we can map this fundamental measurement of the composition of the moon from orbit, or even for the near side of the moon from Earth. And we're looking into potentially, can this detect ice in the polar regions and such as well. So that's what I had for here. I do have background on Mars if I have more time, but if you want to stop, we could stop there. Okay. Okay. Yeah, so this is what I'm doing now on the Mars rover. Now that you have the introduction of how this whole process works, it would be great if we had a microwave radiometer on Mars. We don't, but the new Mars rover, Mars 2020, does have a ground penetrating radar. Ground penetrating radar, it basically sends out a signal and then looks for reflections back at all these different frequencies. But this ground penetrating radar has what's called a passive radiometry mode, where it has an internal calibration source that it can switch back and forth to. And so it does work as a crude microwave radiometer. And so that was basically my proposal to join the Mars rover mission. Here's where Mars 2020 landed. And InSight had a geothermal heat flow probe drill. I don't know if you've been paying, which was, I was a co-I on that instrument as well, built by the German Space Agency, which if you've been paying attention to the news, it unfortunately only got to about 30 centimeters deep, right? It was showing we need to get to something like 3 meters deep to actually measure the geothermal gradient on Mars. So it's kind of sad. People worked for 15 years to get the thing to go to Mars. It got there. We tried really hard to get it down, but it did not burrow to depth. And so that's why, kind of making lemonade out of that situation, we can use all the same models we developed for InSight to try to understand this measurement from the Mars 2020 instrument. And a lot of the same models, I showed you that picture early on about the shadows caused by the lander. Here I can do those same models of the rover, and we could predict what the temperatures as a function of depth will be. And now with the much lower frequencies we have on this ground penetrating radar, which go down to 150 megahertz, we can see quite deep. into the surface of Mars. The loss is a little higher on Mars than on the moon, but we're still seeing probably 10 plus meters deep. And so with that, we're expecting that we could see different heat as a function of depth, different brightness temperatures as a function of frequency with the instrument. And the first data is coming in. We got like a few data points and they seem kind of along those lines. We actually get a really good opportunity because this is a measurement that we want to do really when we're sitting in one place for a long time. We can integrate over a long time, which every other instrument wants to drive around and shoot lasers and things and grind rocks and such. But there's a period called conjunction coming up where Mars actually goes on the other side of the sun from the Earth. Comes up in about 3 weeks, I think. And that is a time where the rover is out of communication with the Earth for about 2.5 weeks. And so during that time, we're going to be sitting and integrating and doing this measurement at about 10 frequencies over this band here. So hopefully a month from now, we have some really neat new data. Yeah, and so one of the things we can also measure is the soil properties and how the ground is warming up over time from the presence of the rover. And yeah, this is all extra stuff I didn't need to show. But anyway, here's what we would expect to measure, for instance, over time. So this was now that geothermal gradient. Here's the day-night cycle. We could see it at the higher frequencies, but not at the lower frequencies. And then as we heat the surface by the rover sitting there, because the rover has a hot radiogenic isotope heat source, we should see it warming over time. So this is the observation we're hoping to take on Mars coming up in the next weeks here. I don't think I really had anything too much else to show there. I guess this is just an example of what that would look like at 2 different geothermal heat fluxes. So we can see, hopefully we can measure that kind of difference. Yeah, you had.
Sorry,
That's okay, it's great.
do you expect any heat transfer to the atmosphere of Mars?
Yeah, there is some, but Mars' atmosphere is about as dense as our atmosphere is at about 150,000 feet. So it's very thin. It's about 1,000 times thinner than the atmosphere here in this room. And so there's not much conductive or convective heat transfer through the atmosphere. So it's mostly, you can use the same kind of radiative models, but there is some heat transfer through the gas. And that's what's kind of interesting. It's the heat transfer through the soil is also mostly dependent on that heat transfer through the gas. And the pressure of Mars's atmosphere is right at some boundary where you go from what's called Fickian to Knudsen diffusion. And so it's right at that controls the thermal conductivity of the material. And so there are some times on Mars's history where the atmospheric pressure was different and it would change the way the heat flowed through the soil pretty dramatically. And that's actually a complication in this. I know I have to exit from the slideshow, see if I included slides like that in here. No, I don't have that in here, but basically Mars's climate history is actually going to be recorded in this heat flux measurement if you really did it super precisely. Yeah, that's actually been a proposed, about the Maunder minimum on Earth, where during the Middle Ages there was a period where there weren't sunspots, and it looks like Europe was a couple degrees colder. One of the tests to see, if that whole thing all holds together and it was really colder because of the sun changing versus there's been some people that say, oh, it was cloud cover changed because you didn't have as much solar activity, is to, if you could really precisely measure the temperature as a function of depth on the moon, then you could see that bump in the history of the heat conducting down. You could actually measure things like that, but those are very small changes. Okay, well, yeah, I already showed you my extra slides, so I don't.
Well, let's go ahead and thank Matthew, and then we'll do some more questions. So thank you.
All right, thank you.
For helping me out here.
this is where he played it safe that I was not on my own computer, so I didn't go to back up to other presentations to show you.
5 hours later.
Yeah, yeah.
Right, yeah. All right, so let's start with folks online. Any questions from anyone online? Just go ahead and raise your hand if you have a question. Okay, I don't see a hand. Anyone in the room have a question? Oh, yeah, Mr.
Does the radiometry method have the capability to tell the difference between isotopic or different types of water, like frozen ice with different water isotopes? Because I know from other talks that you can do kind of the history of cometary impacts and the origin of comets based on the water isotope ratio. Is that something this can go or not really?
So not at these low frequencies like I'm looking at to see deep, but high frequency microwave radiometry was actually used on the Rosetta mission to the comet. They had a high frequency microwave spectrometer that looked at, I think it's 562 gigahertz. And what's cool about that is there's when you have water in vapor form, which you could get if you like crashed a rocket into the poles of the moon, which we did before about 10 years ago, and maybe we'll do it again. But if you observed it with one of these microwave instruments, or you observed the comet with the microwave instrument, the water vapor has a rotational band there. And what's cool is that if you have different isotopes, your oxygen, for instance, in there, you'll actually rotate at a slightly different frequency. And so you'll see that wavelength shift. And so you could see a peak for, if you have a really precise microwave spectrum over that band, you could see the water with O16 and the water with O18 and the water with O17, which is what they didn't, I think they didn't quite get the O17 measurement as well as they hoped with the Rosetta instrument. But that's, so that is certainly a thing you could do, but with higher frequency microwaves and what we're talking about here. So yeah, so that would probably be a separate instrument than this. You could imagine a really super broadband instrument, but for those higher, so we have our instrument we're developing has 4,000 channels between 6 gigahertz and sort of 300 megahertz. But that would be very low resolution as far as a spectrometer where you want thousands over a short wavelength band.
Okay, any other questions? All right, I'm going to ask one then.
Sure.
So you mentioned that CubeSat. Tempest, was that the name of
Yeah.
it? And it's already in orbit around Earth. So is it just a matter of orienting it and pointing it at the moon? Or is that a technical challenge to do that?
I mean, basically, it's a matter of spatial resolution, right? So the 90 gigahertz maps I showed from Greenbank on the giant Greenbank telescope was about the same distance from the moon as Tempest, right?
Yeah.
We're
Right.
about 20 kilometers resolution. So now you can imagine taking the resolution loss when your telescope is this big. Yeah, in order to get high resolution with that, you need to be orbiting the moon.
Okay, but Tempest can't be put in orbit around the moon. Or
Yeah, I
can
mean, it doesn't have to
Yeah,
do
okay.
so, but
Yeah,
I mean, the same way the space station can be put around the moon.
If you have enough
if
fuel
you
and
attach a
time.
rocket to it,
Right,
you get
sure.
there, but-
Okay, but I mean, that CubeSat really is stuck in orbit around the Earth.
Yeah.
So it's really a matter of, it's a small aperture for observing the moon. And that becomes your limiting problem.
Yeah,
Okay,
but I suppose it could turn and look at the moon as probably just as a point source.
okay, interesting, okay. All right.
Yeah, we actually,
Yeah.
the one interesting thing of that, we tried to lobby for, was it WMAP and an official to look at the moon in some of these frequencies for this same reason, because that
Yeah.
could get really high.
I'm assuming that wasn't successful.
No.
Yeah.
Plonk, I mean, plonk.
Fine,
Plonk,
okay,
yeah.
okay.
And then when that didn't work, we tried to, after the L-cross impact in the pole of the moon,
Yeah,
we did really push for WMAP to collide it into the pole of the moon to
Wow.
create another plume, but
Yeah, I can see
It
how,
ended up, they kept it in a parking orbit.
yeah, I can
instead.
see how that wouldn't have played well with the collaboration. Probably. It's not probably how they imagined.
So
it ending.
this is how we think of these big astrophysical observatories as things we could crash into
Yeah,
the moon.
can we smash it into the moon is really the fundamental question. Okay, so now I know what to watch out for with you guys. All right.
Don't run out of cryogen. We'll smash you in the moon.
Any other questions about things we could smash into the moon or Mars if we're thinking big? Okay, I don't see anything else, so let's thank Matthew one more time and we'll close out for today. Thank you.